Hi, good afternoon. What we're going to do today is we're going to talk about approximate integration. And this is section 7.7 from your Stewart book. Now, with approximate integration, we've already seen approximate integration if you took Calculus 1 at PCC. So, really quickly, I'm going to recall some of that integration that we've seen before that is approximate integration from Calc 1. So we have what is known as your left endpoints. All right. So here we say left endpoint, and these left endpoints were given by this summation where I is equal to 1 beginning at n, and this was f of x sub I minus 1 times delta x. We had our right endpoints, and these right endpoints were given by r sub n is given by the summation from I starting at 1, and this is for x sub I multiplied by delta x, and then we had midpoints. And these midpoints were given by m sub n, which is, here we go, m sub n, which is the integration of I beginning at 1, and this is for all of your midpoints for all the sample points multiplied by delta x. All right, so again, these are all from Calc 1. These were all approximations for these integrals that we were working with. All right, we would take all of these intervals, and we would then use delta x as our b minus a divided by n. Meaning, as long as I give you an interval and I give you a certain amount that I want you to subdivide by, we can then talk about that subdivision in making these rectangular sections. That way we can find the area of those rectangular sections. So all of this was based upon rectangles. All right. So really quickly, I'm going to give you a quick breakdown as to what that integration looked like, or what that approximation looked like. All right, so here I have my friend GeoGebra here, and as you'll see, I have this function that I input, which was 0.4 x squared plus 1. In other words, this parabola shifted up by 1 and scaled by a factor of 0.4. And then I gave an n value, which was the n value was going to be 5. All right, so what I'm going to do at this point in time is I want to start playing with this interval, and I want to start moving this interval around so I can say, okay, well, let's start looking at this interval here. This interval is going to go from 0 to 4. Now, my n value currently sits at 1, but again, I want 5 of them. So all I have to do is drag this slider over to show all of these 5. And notice the option is split right here on left-hand sum. So if you notice, the integral from 0 to 4 for this function would be an exact integral, but the left-hand sum here would just only approximate that integral. All right, because again, we have these other little areas here that we don't really get to account for when we're talking about the area underneath that curve. So that's for the left-hand sum. Now, let's look at the right-hand sum. The right-hand sum using these 5 intervals will give us an over approximation. Now, it depends, again, as what your function is doing, if it's increasing or if it's decreasing, whether these approximations are going to over approximate or under approximate. All right, so this is what the right-hand sum would look like. And again, because on this portion of the screen, this function is increasing, the right-hand sum will automatically over approximate. Now, what if we looked at the midpoint? The midpoint actually gives us a little bit more clear view as to what we kind of want to see. But again, all of this is based off of rectangles. We have rectangles for the left-hand sum, we have rectangles for the midpoint, and then we have rectangles for the right-hand sum. And again, these are all of the different approximations that we know so far. And again, that was according to Calc 1. And so what we want to do in this particular section is we want to build upon what we know. And the way we're going to build upon what we know is by still using that whole process known as your Riemann sum. That Riemann sum is that application to the integral that we initially got. That way we can develop the integral a little bit more freely. All right. All we need to then do is just identify what is our function and what is the interval that we're looking at. So here's this function that I'm going to be working with, called it f of x. And what I'm going to do is I'm going to start the exact same way as I did before back in Calc 1, where I'm going to take some random interval, let's say from a to b, and then I'm going to start subdividing this interval. Call this x sub 0, call this x sub n, and then let's start our subdivision. Now, when you start the subdivision, this will be x sub 1, x sub 2, x sub 3, and we'll call this x sub I, and we'll keep it going from there. All right? And actually, you know what? I have technology here. I don't need to stop there. X sub 4, and then we'll go dot, 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 x sub I, dot, 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 and this is x sub n minus 1. Perfect. All right, so what our purpose here is that what we want to do is we want to find all of these outputs. So we want to find all of these outputs when we're looking at these specific intervals. Now, very similar to what we did before, each interval here, each interval will be delta x, and that delta x was defined by b minus a over n. So every single interval that we are working with is always going to be delta x. And the reason we want to identify this is because now that we've defined these intervals that we've, let's say, subdivided, what I want to do now is I want to create these heights. But again, we're not creating rectangles. What we want to do instead is we want to work with these guys. Go from there and go from there. All right. Now, what does this look like then? Well, if we start looking at this, at one of them, we'll highlight this here, and then I'm going to extract that for this area here. Looking at one of those, we have something that looks like this. Which is a trapezoid. So we want to make sure that we're using this trapezoid figure to estimate this area. Now, this part here, the base here was delta x. All right, that was from the bottom down there. Now, the heights here that we're going to be looking at, one of the heights was this one here, which was f of That was f of x sub 2, and that up here was f of x sub 1. Now, height-wise, that means that this length, that height, is just f of x sub 2. This height here was f of x sub 1. Great. Now, in order for us to be talking about the area of a trapezoid, oops, excuse me there, oops, f of x sub 1, and then this one here. So the area of a trapezoid is given by 1/2 multiplied by the height multiplied by base 1 plus base 2. Base 1 and base 2 are the parallel sides for any trapezoid. So what are those parallel sides? Well, the parallel sides for us are these two, which means that for our function, the one that we're working with here, the area of this trapezoid down here is just going to be 1/2 multiplied by the height, but the height goes from one of the parallel sides to the other. It's the one that's perpendicular to both. Can you see one side that's perpendicular to both? Sure. That's delta x. That's our height. Base 1 and base 2. Well, base 1 is, let's call it function of x1. Base 2 is that function of x2. Which means we found this area of the trapezoid, which was the area of this initial trapezoid. Awesome. But there's an issue with that, and the issue is that it doesn't approximate all of the area under the curve. This only approximates that one trapezoid. So what do we want to do instead? Well, we want to start expanding this for all of the smaller trapezoids. So let's start expanding this into all of the smaller trapezoids. All right, I have one here, one here, one here, one here. All right, and I'm going to start highlighting them. Like such. All right, so I'm going to say to approximate the area under f of x, and let's say using trapezoids, then we're going to say that the area is just going to be the summation of all of the individual trapezoids. Well, let's go through those calculations here. Would you agree that that's just 1/2 multiplied by delta x, and then f of x naught plus f of x1? That's the first trapezoid here. Plus the second trapezoid, that's the one that we found over here. That was the purple one. So plus the area of that purple trapezoid, and that was f of x sub 1 plus f of x sub 2. Plus, we can do the area of the third trapezoid, delta x, and that's going to be f of x sub 2 plus f of x sub 3. Now notice, we can keep going because all of this keeps going to to x sub n. So if you notice, there kind of looks like there's a pattern here where we can keep going, and once we keep going, we're going to get here to 1/2 delta x multiplied by f of x sub n minus 1 plus f of x sub n. And that's our stopping point. Now, once we have all this, well, we can actually re-index, or not re-index, we can actually reshuffle all of this. Notice that every single term has a 1/2 delta x. Now, because every single term has a 1/2 delta x, I'm going to factor that out. So I'm going to say that this is all equal to 1/2 delta x. What remains here is just f of x sub naught plus f of x1 plus f of x1 again plus f of x2 plus, hey, there's f of x2 again, plus f of x3. And then this is all just plus dot 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 plus f of x sub n minus 1 plus f of x sub n. And so all I need to do now is just condense all of this. Well, the condensing of all of this actually makes it real nice and easy, which means this is going to be just f of x sub naught plus 2 of the quantities for f of x sub 1 plus 2 of the quantities for x sub 2, and we keep going, plus 2 of the quantities for x sub 3 plus dot 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 plus 2 of the quantities for f sub x minus 1, because the term previous to this would have also had another f sub x n minus 1, and then finally we only have f of x sub n. Here we are. This here is known as our trapezoidal rule for t sub n. So when we want to work with the trapezoidal rule, it's going to be listed here. All right. Now let's formalize this just a little bit more. All right. So I'm going to write the quick outline for this rule, and then you can go ahead and copy it down. So here's your trapezoidal rule, where we want to approximate the integral for this function on the given interval. Then using the trapezoidal rule, here's the notation that we use. This is capital T sub n, and then we're going to use the rest of the formula to make sure that we illustrate this. Now, how does this look like visually? Well, let's go back to that one example that we were looking at to see if we can then translate this into a visual representation for the trapezoidal rule. All right, so here, once again, we see that same example that we started with when we were looking at this left-hand sum, midpoints, and right-hand sum. Now, we want to now start looking at this same example, but now let's use trapezoids. So I'm going to look at my trapezoids here, and I can start reducing the amount of trapezoids that I see here. All right, I can start seeing the amount of trapezoids that I see here, which is going to be awesome. All right, now let's see if I can hide this really quick. Give me one quick second. All right, here we are. So I went ahead and I removed now the rectangle, so we won't be able to see the rectangles anymore, and that's good. Now let's look at the trapezoids. Look at how much of a better approximation these trapezoids actually give us. Now, at this particular time, we only have 5 trapezoids, but even then, looking at these 5 trapezoids, look at the top of their slopes. That's a really good approximation that we start getting for this parabola. So when we start looking at the trapezoidal rule, we want to make sure that using this trapezoidal rule that we can start extracting these approximations that are going to give us really good values to approximate these integrals. Because as you've seen before, some of these integrals you won't be able to calculate directly, which means we then need to get approximations for them. All right, so let's go on to an example and let's see how we're going to be using those approximations for those integrals. All right, so here's going to be example number 1. So use the trapezoidal rule to approximate the integral from 0 to 3 for sine of t over t dt, and this is going to be with n is equal to 4. All right, so if n is equal to 4, we're going to go ahead and we're going to get started here. All right, the first thing I want to do is I want to calculate my delta x. Delta x is going to be b minus a. So that's So that's going to be 3 minus 0. So that's 3 minus 0 divided by n, where this n is going to be 4. Which means we get 3/4. Awesome. Now that I get this, what I want to do is I want to start looking at my interval. All right, so really quickly, I'm just going to draw a quick interval here. That way I can start analyzing what numbers I'm going to be looking at. All right, so let's go ahead and let's start with our A value. The A value starts at 0. All right, so 0, this was my A value. And then we go over a delta x value. So that's delta x, which means we're now at 3/4. So this is your x sub 1. We go another 3/4. Let's go here. So what that means is that we're going to take 3/4 and we're going to add another delta x to it, which means we're going to get 3/4 plus 3/4 to give us a total of 3/2. All right, or you could think about it as 6/4. So I want this 3/2. There we are. I'm going to do delta x again. There we go. All right, so delta x, so we're going to take that 3/2, and we're going to add 3/4 to it once again. This time we get 9/4. Now we have one more because again we have 4 different intervals that we want. So that last interval is going to be another delta x. So that's 3/4 plus 9/4. And again, this was x sub 2, this was x sub 3. So the last one's going to be x sub n, which was our b value, which should naturally be 4, and it will be because 9/4 plus 3/4 gets us 12/4, which is just 3. All right, and this is our b value, in other words, our x sub n. All right, now that we have this, let's go ahead and let's start using that approximation. So t sub n, but in this case n is 4. This is going to be 1/2 delta x was 3/4 multiplied by the function evaluated at x sub 0, which is just your first value, in other words, 0, plus 2 times f of x1, that's f of 3/4, plus 2 times f of x2, which is f of 3/2, plus, again, 2 times f of 9/4. And then finally, the last value is 3 for that interval, so we're going to do plus f of 3. Nice. So, let's go through the whole evaluation process then. Working through this evaluation process, we're now going to start seeing this. All right, 1/2 times 3/4, this should be 3/8 multiplied by f sub 0. All right, well, let's look at the function that we have. Let's erase this just a little bit. That way we could be more concise. There we are. So the function that we have here, let's say f of x, or in this case f of t. Let me make sure we use the correct variables. There we go. F of t is just sine of t divided by t. All right. So let's go through it. All right. So now I actually want to let's say I want to take back a piece here. Now, the only reason I'm saying that I want to take back a piece is because as I start looking at my function and this value here, it looks like my function is going to be undefined at this particular value, or it's going to get us an indeterminate form. And we don't want to use an indeterminate form at this time. So instead, what I'm going to do is I'm going to give you a different function for us to be able to work with. All right. So instead of this function, that way I don't have to change my interval around again. I want to actually work with a different function. Let's not make this sine of t over t, which, I mean, it's a really good question, but it would cause me to re-index my interval again, and that would just be a really big pain. All right, so let's work with the function of, I don't know, let's say x squared. All right, make this nice, straightforward. All right, so if the function that we're working with, oops, cheese and crackers, man. So f of t is t squared. There we go. So now using this function, what I want to do is I want to insert all of my values here, all of those intervals that I found, or the endpoints for those intervals. So all I'm going to do is type in or input f of 0. So naturally f of 0 here just becomes 0 plus 2 times 3/4. 3/4 here becomes 9/16 plus 2 times 3/2. 3/2 here becomes 9/4 plus 2 times 9/4 in here becomes 81/16 plus f of 3. 3 in the function becomes 9. So we get this. And all we have to do at this point in time is simplify and make sure that we can add everything together. All right, this will be 9/8 plus, let's make this 18/4, and we can modify these in a little bit, plus that's going to be 81/8 plus 9. All right, not too bad. So all I'm going to do is I'm going to take my calculator and I'm going to start finding out what are these, or what do these fractions add up to. So 81 divided by 8, and then we're going to add 9. So this should give me somewhere along the lines of 3/8 multiplied by 99 divided by 4. Nice. And then at the end, all we do is multiply by 3/8. Now, multiplying by 3/8 should get me 297 divided by 32. Now, as an approximation, we should get 9.28125. Nice. So, to summarize here, the integral from 0 to 3 for t squared dt gets me an approximation of 9.28125. That's a pretty good approximation. All right. So when we get this approximation, again, it's not the exact value, but it should be a good indication of what it is. Now, the actual amount, and I'm going to write this in a different color, the actual amount from 0 to 3 for t squared dt is in fact just 9. Now notice the approximation. The approximation is a pretty good approximation, but again, there is some error that was introduced. All right, so we then must talk about that error. So we get some error here. And working with this error, I want to work with absolute error. Absolute error just means that we're going to talk about error in this, let's say, positive aspect. All right. So when I'm looking at this, I'm going to be looking at 9.28125 minus the actual value, which was 9. All right. So when I do this 9.28125 minus 9, it should just get me the decimal value here of 0.28125. And this is my error. Now, what does the error then transcribe into? Well, if we look at it as a percentage, that's my error for this approximation. So, 28% of this is not approximated. That's the error that's off. The rest of it is approximated. The other 72 something or other is approximated. All right. So we have to then make sure that if we want to use the trapezoidal rule, that we can start by analyzing the error that will occur. All right. All right. So now that we have this whole idea of approximating integrals using the trapezoidal rule and finding that error, now we want to switch our attention to Simpsons rule. All right. Now, Simpsons rule, he actually took a different approach, which is really interesting to see. That his approximations don't rely on rectangles nor trapezoids. His approximations for Simpsons rule actually just rely on parabolas. So, Simpsons rule relies on parabolas, and I'm going to try to give you a visual representation of what he was looking at when he was developing this. Alright, there we are. Let's get an axis going here. Once we get this axis, then we'll be able to get this illustration going for us. There we are. Let's hide that. Perfect. That's our y, and this is our x. And so, again, what we want to start with is a certain function. So let's start by drawing some function here. Let's say our function does that. Let's call this f of x. And let's start cutting this function into smaller pieces here. So we're going to have a, which is our x naught. Then we'll have x1. Then we'll have x2. Then we'll have x3, so on and so forth. X sub I. And we'll have some x sub n minus 1. And then we'll have some x sub n. Alright, and what I'm doing is I'm putting these points that are being generated out in the Cartesian coordinate system. Now, what he was looking at was he saw that as we were partitioning this interval going from A to B, that as long as your interval was partitioned an even amount, meaning that the n values had to be even, so n must be even. Anytime that n was even, then he could create this parabola that went through 3 of the points. All right, so how does that look like? Well, these 3 points here would contain some sort of parabola. Let's say it look like this. Coming down this way. And coming down this way. So some form of a parabola this way, where the part in question, or the parabola in question, we would then generate this area. Now, a different set of 3 points again would generate again another parabola once again. So as we start looking at this, all we're doing is we're just taking a whole bunch of these parabolas and we're trying to find the area that's being generated by these 3 parabolas that are underneath this given curve. Now that is pretty amazing there. Now the parabolas, again, for the sake that we have here, could look like this. All right, and that was again finding the area underneath that curve. There we are. And then the last of the parabolas, we'll do this again in orange. This parabola here that would contain these 3 would look something like this. All right, bear with me on that. And that's why n had to be even, because if n was even when we build this parabola, where one of the parabolas ends, that's going to be the beginning of a different parabola. Now, looking at these polynomial functions that we could approximate, then it just becomes a natural sense to just say, yeah, we could build parabolas through 3 given points, because any parabola can be found by just identifying any 3 specific points. So any parabola can be found by identifying 3 different points. And that's all we need. So when we're using Simpsons rule is just gonna streamline that. All right. So let's go ahead and let's formalize this. All right. So I'm going to formalize this really quick, and then you guys will go through and write it down. All right, so here is Simpsons rule. Simpsons rule states that if we want to approximate this integral, then what we have to do then is go through the process of identifying our interval. Delta x is defined as it always is. However, the one specific attribute that we need here is that n needs to be even. N needs to be even in order for this to work. If n is not even, we cannot use Simpsons rule. So it must be even, the amount that we cut our interval into. So what we're going to do is we're going to use the same approximation. So we're going to go with this one here, that we want to use Simpsons rule. So use Simpsons rule to approximate the integral, let's say from 0 to 3, and let's stay consistent with the previous example, from let's say from 0 to 3, and this is going to be for t squared dt, with n being equal to 4. Alright, so here we go. So let's go through that quick subdivision once again. So that subdivision here was 3 minus 0, and we're going to divide it by 4, so that's going to be 3/4. And again, working with the same interval, then we're going to be able to extract all the exact same values that we were looking at last time. But just for consistency, I want to make sure that we illustrate them once again. So the first one here is 0, that's where we start. That was our starting point, 0. Then we increment to 3/4. Then we increment again another 3/4, another delta x. All right, I believe that one was 3/2. Then we increment again another one, all right, which I believe gets us somewhere along the lines of 9/4. And then we finally get to the other one, which is the very last one, which was 3. In other words, 12/4. All right, so let's go through and let's start using Simpsons rule. Simpsons rule, this is going to be the approximation. The notation is just capital S for Simpson. So Simpsons rule, we're using 4 as our increment. We're going to take this 1/3 multiplied by delta x. Delta x is 3/4. And we're going to multiply by the function of 0 plus 4 times the function at x1, which is 3/4, plus 2 times the function at 3/2, plus 4 times the function at 9/4, and then finally plus the function at 3. Great. So all I have to do is evaluate using the function that I was given here, which is that f of t is t squared. So let's work through this really quick. In here, that's going to be what, 1/4? That's not too bad. F of 0, that's just going to be 0, plus 4 times 3/4 squared, that's going to be 9/16. plus 2 times 3/2 squared, that's going to be 9/4, plus 4 multiplied by 81/16, and then finally plus 9. All right, so let's go through this. That's 1/4 multiplied by, let's see, that's going to be 9/4 plus, what's that, 9/2 plus 81 divided by 4, and then plus 9. All right, so all I'm going to do is I'm going to go to my calculator, and I'm going to start entering all of these values, plus 81 divided by 4, and then plus 9. There we are. So I get 36 right in here, so this is 1/4 multiplied by 36, and this actually gets us 9, which, if you remember, that is the exact answer. All right, so why did Simpsons' rule then give us this exact answer and not an approximation? Well, Simpsons' rule, remember, is built upon parabolas, which means if it's built around parabolas and we want to approximate a parabola, then every 3 points that we select will then automatically be modeled by the parabola that they initially sit on. In this case, t squared. So naturally, when we're approximating using Simpsons' rule for a parabola, it's going to give us the exact value. But we're not going to be approximating a parabola when we're doing our integration on an exam. That's when we're going to be looking at a little bit more interesting functions. All right. So if we wanted to find the error here, again, we can always find that absolute error. All right. So next, I'm going to talk about the error bounds for Simpsons' rule and the trapezoidal rule. All right. I'm going to write those bounds in just a bit. That way you can see them on your screen. All right, so here on the screen right now, you have the error estimates for the trapezoidal and Simpsons rule. The first paragraph that we look at is going to be that the trapezoidal rule's error that we're observing. This is that if the second derivative of the function is continuous and capital M is any upper bound for the values of the magnitude, or sorry, the absolute value of the second derivative on the interval from a to b, then the error in the trapezoidal approximation for the integral will be given by this formula here. All right. Now, very similar, we're going to see the next process is going to be for Simpsons' rule. Now, when we use this one for Simpsons' rule, again, we have to then make sure that the fourth derivative here must be continuous. So very, very important. Error estimates for Simpsons and trapezoidal are different, and we have to make sure that we use the correct ones. Now, let's look at an example really quick to outline this. All right, so in this example, we want to find an upper bound for the error in estimating the integral from 0 to 2, and this is for 5x to the 4th dx using Simpsons' rule. So again, we're going to be using Simpsons' rule here, and Simpsons' rule then states that we have to look at the fourth derivative. So looking at the function that we are given, which is 5x to the 4th, we need to look at the fourth derivative here. So first derivative, would you all agree that's just 20x third? Second derivative, would you all agree that's 60x squared? Third derivative, would you all agree that's 120x? And finally, the fourth derivative is just 120. All right, so we have that the fourth derivative is continuous. Now all we need to do is just develop this upper bound. So we have to make sure that we bound that specific derivative. Bound by largest number. I'm going to abbreviate number as this pound. So bound the largest number bound the largest number for the given interval. And again, the interval goes from 0 to 2. That's the interval that was given. All right, that's the interval that was given right up here for that integral. So notice this doesn't have a variable, but if it did have a variable, I would just insert one of these values that would make this function the largest amount. Therefore, I can approximate it using that upper bound estimate. All right, so now I can then start saying, hey, let's start looking at this error for this integral using Simpsons rule. So the upper bound here is 120 because, again, I don't have any variables to insert here, which means at this point in time, it's just going to be that maximum amount of 120. So that's 120 times b minus a. So b minus a, that's just going to be 2 minus 0 raised to the power of 5 divided by 180 divided by, 180 multiplied by n to the power of 4. So we need some n value. All right, now, I didn't use the n value here. All right, so use n is equal to 4. There we go. Fixed. So we're going to do now 4 to the power of 4, and that'll then multiply it. All right, so let's go through all of this process then. This would mean that this is what, 120 times 2 to the power of 5, that'll get us 32, and this is going to be 180 times 4 to the power of 4. Let's see if we can simplify all this. I believe this simplifies down to 1/12, which means that the error for Simpsons rule, if we were to use n is equal to 4, we would get this error here. All right, and again, that would be the difference in between the approximation and the true value for that integral. So without actually doing the integration, we're actually just finding the error and seeing which n value would get us a more accurate approximation. The smaller the error, the better the approximation is. All right, now let's look at a different example. All right, so on this example, let's see if we can take it up a notch. So we want to estimate the minimum number of subintervals needed to approximate the integral used in the previous example with an error of magnitude less than 10 to the power of negative 4. All right, so here we go. So we want to, again, use the example that was given to us above in this previous example. So I'm going to write down all of the constraints that were given here. We're given the integral from 0 to 2. So that's from 0 to 2, and that's 5x to the 4th dx. We're using Simpsons rule. So Simpsons rule, and we're using a subdivision of 4. There we are. So Simpsons rule, subdivision of 4, and we have that integral. Awesome. So let's see if we can go through this example now. All right. I'm going to use one more thing. I'm also going to use the error. The error bound for Simpsons rule is going to bound it this way, b minus a to the power of 5 divided by 180 multiplied by n to the power of 4, if I'm not mistaken. There we are. Good. All right. So what do I need to occur here? All right. So what we want is we want to estimate the number of subintervals. So we want to find n. That's our goal. So the goal is to find, n. That's our goal, which means we must be given some error and we must be given some of these values. All right. So I want my error, whatever this error is, and remember, this is what finds the error. Whatever this error is, I want it to be less than 10 to the power of negative 4. There we go. So what I'm looking at is this error, or in other words, this error needs to be less than this. Awesome. So let's work through it. All right. So we have some values that we can look at from the previous example. So from the previous example, we get an upper bound of 120. Now that's going to be nice. We're going to be able to use this. So that's going to be So that's now going to be 120 multiplied by b minus a. That was that 2 minus 0 raised to the power of 5 divided by 180 times n to the 4th must be less than 10 to the power of negative 4. Now let's see if we can work through some simplification here. All right. Again, we're trying to solve for n, so we're going to make sure that we solve for n. Remember, n is always going to be positive, so we got to keep that in mind. All right. So let's see. I want to multiply both sides by n. So that's going to be 120 multiplied by 2 to the power of 5 divided by, that's going to be 180. And I'm going to divide both sides by 10 to the power of negative 4, just like that. Awesome. All right, and this is going to be less than n to the 4th. Good. All right, let's see, 120 divided by 180. I do believe that simplifies to about 2/3. So that's going to be 2 multiplied by 2 to the power of 5, and that's going to be 3 multiplied by 10 to the power of negative 4. And we'll clean this up just a bit in a little bit. All right, and this is all, this is all still less than n to the power of 4. All right, so then that's really just 2 to the power of 6 multiplied by 10 to the power of 4, because that had a negative, divided by 3. Nice. And that's still less than n to the 4th. Now I need to solve this n value. So to solve this n value, what I'm going to do is I'm going to take the nth root of both sides, or the 4th root of both sides. So I'm going to take the 4th root of 2 to the power of 6, 10 to the power of 4 divided by 3, and this is going to be less than or equal to n, or just less than n. Now all I'm going to do is substitute this into the calculator. So what I get here is that 21.5, 21.5 is going to be less than n. There we are. So remember, for Simpsons rule, n must be even. This one's not even. How do we alleviate that? Well, let's make it a little bit more concise. The minimum number of subintervals needed is n is equal to 22. If we over approximate, so if we get n is equal to 22, that's going to tell us that we get a little bit better approximation, which means it's going to lessen our error a little bit more, which is what we want. So if n is equal to 22, then our error will definitely be less than 10 to the power of negative 4. 10 to the power of negative 4, that's a really, really small error. And again, trying to approximate that error, well, we now know that we need 22 subdivisions. Now again, this is a little bit better when we start working with computer programming, because if you take numerical methods, which if you're some form of an engineer, you probably will take numerical methods, which means that you need to work with these numerical integration techniques. That way you know how to approximate your bounds, or you know how to approximate your subintervals given a certain error bound that you want to meet. All right, so that now wraps it up for this section. I hope you enjoyed this section, and we'll start on the next one shortly. I'll see you then.